Okay, so this is for ECE 4305 for the fall of 2021, and this is lab 5, the asymmetric FIFO buffer. So in this lab we have an asymmetric FIFO buffer in which the write data is twice the size of the read data. So in this case, uh, I put my write data as 16-bit value, and then my read data as an 8-bit value. And I based my memory size off the read data, so we're going to have 8-bit words, and then I just decided to choose 8 locations so it's easy to show up on the test bench. Um, and we could see here that our write data is 16-bit value. So to start this test bench, I reset, meaning that our um, write address is 0 and our read address is 0. And I also chose the little endian standard to store the write values. So this lower byte of 0f is going to be stored in the first memory address, and then this most significant byte f0 is going to be stored at the first memory address. And this is because I set write high. This is like a write enable. You can see here that that was immediately written to memory. And since this is the first word fall through FIFO buffer, we can see here that this 0f is shown once it's immediately written to. Then we decide to read from a few values, and since we already have this first word, once we pop that and go to the next value and then pop that, we're going to be at this uh, unknown value at this second memory address. So this is just some garbage value. We decided to reset after that test. And then we're going to treat this as a garbage value because we reset our memory, so this is a valid location to write to. So we're going to fill the first 6 locations with FF00, and then we're going to change our write data to AA. And this was just so it's easier to see that once we're full, so at this point right here, we could see that we're able to write AA, but then after that clock cycle, we could see that it doesn't overwrite any more of the memory values. That's because it's full. And then in this test, we're also going to show that once we decide to read one of those values, we're still full because you need 2 memory locations available for the write data to be passed into. Then after that, we decided to reset again. You can also see after we got to this second place that we're not full anymore. But once we reset again, we're going to be reading and writing at different speeds in this spot right here. So we could see that we initially write, so we're going to be writing in 4 values. So I just made this easy to see, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. And then we're going to be reading a few values, and we can see that we have 0, 1 at our output. Then we're going to read 0, 2, and then 0, 3. And then after we read 0, 3, we're going to write 0, 5, 0, 6, and then 0, 7, 0, 8. That in our memory down here. Then after that, we're going to read one value. We could see that we went from 3 to 4. And then after that, we decided to write 090A into our memory, which is at these locations right here, because these are valid since our read pointer is now at 3. But also since our read pointer is at 3 and our write pointer is at 2, we can see that we don't have enough memory space to continue writing. So we don't write in this 0C, 0B value, nor this 0E, 0D value. And then after that, we decided to read a couple more values, and we can see that we have 0, 0, 5, 0, 6 at the output. After that test, we reset again, and then we decided to test the write and read simultaneously, and we could see here that we had 8811, then BBA, and then DDCC, and this is just to see what's being overwritten when and what situations they occur in. So since we have first word fall through, we're going to have 8811 written to, increment our write address by 2, have 88, 11, 88, or 11, 88, 11, 88, 11, 88. And then we're full at this point right here because our write address is 4 and our read address is 5. And then there's a full value right here because our read pointer was at 5 going to 6, and this is based on a flip-flop. We're just outputting that previous value saying, hey, we were full. And then after that, due to that as well, we have 7 at this output right here, but we haven't written anything yet because this little flip-flop offset by 1 kind of messed up the timing. But then after that, we were able to write DDCC, and we could see that right here. Then we were able to write to it one more time, and we could see that right here. But then after that, our write pointer's at 0, 0. So once we get to 0, 1, can't write, but then it's going to do the same thing. This is just so it doesn't split up the words. So then we have, so we see BB, have AA, and then, oh, sorry, we have AA, then BB, then AA, and then BB again, and then we're going to be able to write more values after this. So that concludes the lab.